everyone, and today we're going to be reviewing Vector Calculus 2414. Calculus, and I should say today's topic is going to be on vectors and 3D graphing. So, first things first, a vector is simply any object with a magnitude and direction. So when writing out a vector, we can have, so let's say we have vector v, and they're always written in the format of an ordered series of numbers. So some vector in a two-dimensional space could be written as, v, x-coordinate, y-coordinate. Vector in 3D space could be written as x-coordinate, y-coordinate, z-coordinate. And just generally, a vector in n-dimensional space could be written with, 1 to n coordinates. x1, x2, dot, x sub n coordinates. And alternatively, people can also write vectors in this format, so like this, or in the 2D example, we could say x in the ith direction plus y in the jth direction. We almost write these sort of like coefficients. And we don't ever add these together, we keep them separate. And then similarly for 3 dimensions, it'd be x, I, y, j, z, k, and for n-dimensional, this format's a lot less common because there's only so many letters. Vectors. In this class, we're primarily only concerned with vectors in 2 and 3 dimensions. So it's important to know how we place them on a graph. Okay. So, for example, if I wanted to graph the vector 1, 3, the way we put that on a graph is we look at each of the coordinates and we say, okay, well this is its length in the x direction. That's its length in the y direction. If we can almost imagine this is a point, so the point 1, 3 on this graph, 1, 2, 3, about this point. The vector is simply going to look like an arrow being drawn from the origin to the point itself. And that would actually be the graphical representation of this vector. What's that? So that is v. And then similarly, in 3 dimensions, let's say we have vector 2, 2, 2. If I wanted to graph that, I would simply go 2 in the x direction, 1, 2, 2 in the y direction, so that's y, so from here 2, or 1, 2, and then 2 in the z direction, so 2 up, so duh, 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 and it would be, let's see, there. Actually, let me redraw that one. That came out a bit. Let's see, undo. Sorry about that. So X, Y, Z. And again, 2, 2, 2 would be 1, 2 in the X direction, 1, 2 in the Y direction, and then 1, 2 in the Z direction, so 2 up. That would be our point, and that would be the vector heading to that point. So next, let's talk about vector magnitude. As I mentioned before, vectors have both a direction and a magnitude. We just saw how you can, represent their direction by graphing them. Magnitude is a way we can represent the length of the vector. You almost think about it as the length of the arrow we've just drawn. So vector magnitude is normally written as, this operator, magnitude of vector v. Magnitude, or really, in normal terms, just length of vector v. So in the two-dimensional case, let's say we have v, for clarity's sake. So let's say we have vector v is equal to, coordinates v1, v2. In R2, you can almost imagine magnitude as using the distance formula between the coordinates that the vector has and the origin. So it would be v1 minus 0 squared plus v2 minus 0 squared. It's the square root sum of all squared coordinates. So similarly in R3, let's get a three-dimensional vector. In R3, we would have 1 plus u2 squared plus u3 squared. And let's say we have some n-dimensional vector, so that's w1, w2, wn. Then in n dimensions, w's length would be first coordinate squared plus second coordinate squared plus all of the coordinates up to the final one squared, and then square root their sum. And you can imagine what this looks like on a graph. So, let's go back to like that three-dimensional vector we had, 2, 2, 2. X, Y, Z, and as we said, 1, 2, 1, 2, there, and then 1, 2, there. And that was our vector 2, 2, 2. And if we want to find the length of this vector, which you can imagine as the length of this arrow that we've just drawn, that's going to be equivalent to saying square root of first coordinate squared plus second coordinate squared plus the third coordinate squared, which, to doing some algebra, 4 plus 4 plus 4. So it's going to be square root of 12, which, simplified a bit, that is 2 root 3. So that would be the length of this vector right here. It's 2 root 3 units long. Okay. So now we know vectors exist and they have some form of direction and magnitude. And just like numbers, there's certain basic algebra operations we can do with vectors. So the two main ones are vector addition and scalar, or just number. It's another word for number multiplication. So vector addition is just adding to vectors of equal dimension. So for example, adding two, adding two vectors in 2 dimensions, so ones look like this, or adding two vectors in 3 dimensions looks something like this. But you can add two vectors which have different dimensions. So in this example, I couldn't add v and u together. Only v and some other size 2 vector. So, for example, if we have v equals 1, 2, v3, get used to seeing u and v a lot, and u is going to be u1, u2, u3, then v plus u then v plus u, the way we actually add these together is that we add each of the individual elements to each other to create a new vector. So in this example right here, we go for the first column, v1 plus u1, second row of elements, v2 plus u2, and third row of elements, v3 plus u3. And that new vector is the sum of u plus v. So actually, in my definition, I'm just going to mention adding two vectors equal to dimension resulting in a new vector. Because that's what this is, right? We've added u and v together, and their sum is actually a new vector, whose each individual element is just the sum of these individual elements. Scalar multiplication is a bit different in that it actually works between some number, so just like, constant c. So c is not a vector here, c is just some number, 1, 2, 3, a million, -5 halves, whatever, a number. So we have c, and then use v again. Then c times v will look like multiplying c by each of these elements. So c times v is going to be c times v1, c times v2, c times v3. So I'll just say embarrassing against multiplication, but timesing a number and a vector to create a new vector. Because again, that's what happens. I've multiplied c, a constant, times vector v, and the result is a new vector of these same length, 1, 2, 3. But again, the only difference is now each of the individual elements are multiplied by C. So now that we've done some basic algebra with vectors, it's, it will be good to see what that looks like in terms of the graph. So actually, so I'm going to set it up to where we have the algebra taking place, and then graphs taking place. Let's say it's a little table. We'll use 2 dimensions and 3 dimensions. Okay, cool. So let's say the first one, we're just adding 2 vectors, v plus u. And as we said before, v plus u is going to be a new vector whose individual elements are just v2 plus u2, adding them together just results in a new vector. And let's say on base, u and v start out looking like this. So there's v, there's u. Just 2 vectors of a similar size pointing in the positive direction. Or toward the first quadrant, I should say. But how do we graphically represent what v plus u looks like? Because if it's a new vector, we should also be able to graph it. So, and we can imagine, v and u, not perfectly recreated, but there they are. And if I want to see what v plus u would actually looks like, the way we think about it is, imagine taking u Imagine taking u and aligning it so that the starting point of u is put on the final arrow, like the ending point of v. So you can almost imagine u's right here. You can almost imagine dragging it up and placing it right here such that it ends up on the tail of z. We call this adding tip to tail. Well, if you do that, this sort of bigger combined vector, what that points to right there, if we draw a vector going from the origin to where this combined thing is pointing, that vector right here is the same as u plus v. And similarly in R3, if I have v plus u, it's going to be the same as v1 plus u1, v2 plus u2, v3 plus u3, I guess I should draw with them. Let's say v looks like that, and then u is kind of coming out more in this direction. U. Then, again, same way. If I just put u, imagine taking u and putting it on the end of v. So, there's u, it's about in this direction. So let's imagine that got taken and put at the end of v. Then, the point where this new combined vector points to is the same thing as u plus v. Okay, cool. And then similarly, if we do scalar multiplications, let's say c times v, and again, that'll look like, in 2 dimensions, that'll look like c v1, c times v2, and in 3 dimensions, that'll look like c v1, c v2, c v3. In 2 dimensions, the interpretation of what c times v looks like, we can imagine v, it's pointing in this direction. That's not c times v, that's just v. If we can imagine what multiplying c to v does to v, we can almost imagine c is sort of like a scalar that stretches, that stretches or shrinks v itself. So let's say c is some big number, like it's a number that's greater than 1. And what's going to happen is the new vector c times v will be in the exact same direction as v, but stretched out. We can imagine c is actually stretched out v's length. So that'll be c times v. And then similarly, in 3 dimensions, try it one more time. And let's say v looks something like this. Then c times v, again, is just going to stretch or shrink it out. In this case, I'm assuming c is sort of a bigger number, so it's stretching v out. Okay, and then we can even do, we just do a real number example. So, example, let's let v be the vector 1, 2, 1. Let u be the vector 0, 0, 1. And let c be some number, which we'll say in this case is 2. So let then graph u plus v all times. Actually, let's break this up. Graph u, v, u plus v, and c times u. Okay. So first, let's get our basic graph, x, y, and z coordinates. We should be familiar with this. So first things first, let's graph u. So u is the vector 0, 0, 1, which means that on a graph, it looks like it's pointing to the point 0, 0, 1. So that'll be 0 in the x direction, 0 in the y direction, and 1 in the z direction. So that, so u is the vector from the origin to that point. And similarly, v is going to be the arrow pointing to the point 1, so about the same 1 in that direction. 2, so 1, 2, da, 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 da. And then 1 in the z direction. So it's about that high. So high. So that's our point. That will be vector v. Okay. If we want to graph u plus v, we could either do what we just, we showed before. So like, let's say I add them tip to tail. So I'll take u, and I can almost imagine picking it up and placing it at the end of v. So let's say like that. So again, that's about, u is just the vector going one up. So just put that in v. So u, which means the new vector, their sum, should be the point, or should be the vector from the origin to this new point. U plus v. And if we wanted to go the other way about it, we could say, well, what is u plus v? U plus v is going to be 1, 2, negative 1, right? V plus u, 0, 0, 1. So adding them together results in, we can actually just go back and do the algebra from, if you remember, adding two vectors is the same as just adding each of their individual coordinates. So adding u plus v is adding this coordinate plus that coordinate, 1 plus 0, this coordinate plus that coordinate, 2 plus 0, negative 1 plus 1, which results in 1, 2, let's see, oh, I made a small mistake here. I think I read v as 1. This is when I was graphing it. I read it as 1, 2, 1. So so let's just pretend it was always 1, 2, 1. Okay, so okay, good. So 1, 2, 2, which, if we were to graph, think about graphing this out, that would be 1 in this direction, 2 in the y direction, so 1, 2, so 2, and then 2 in the z direction. Well, 1, 2, which again gets us to the point u plus v. And then similarly, or finally, if I were to multiply c, I mean it's u plus v, c times u, that's going to be the same as multiplying c, which is 2, times 0, 0, 1. And again, what vector is that? That's just going to be 2 times each of these components. So 2 times 0, 2 times 0, 2 times 1, which is 2 times 0 is 0, so 0, 0, 2. And if we chart that one out, 0, 0, 2 is going to be, let's see, 1, 2, about this vector right here. So c times u. Sorry, I want to adjust this drawing just for like a good size. I think that's nice. Okay. Better type these out. I should be better to type these out. So let's say in this section we just want to focus on, let's see, unit vectors and angles between vectors. Okay, So as we said a couple times, all vectors have some magnitude, which is essentially just the length of the arrow we're drawing. So definition, a unit vector is a vector with magnitude specifically 1. So a unit vector is just any vector whose length is exactly 1. So, for example, I can say the vector 1 over root 2, 1 over root 2 is a unit vector. And how can I prove that's true? Well, I can just take its magnitude. So the magnitude of 1 over root 2, 1 over root 2, and show that its magnitude is equal to what? It needs to be equal to 1. So if we remember going back, the way we find vector magnitude is we sum up all of the individual terms squared. So in this instance, we can see that if I, working on the inside, we have square root of 1 over root 2 squared is the same as 1 squared, 1 over root 2 squared, 2. Same right here. 1/2 plus 1/2 is 1, and then square root of 1 is 1. So I've just demonstrated that this vector is unit. Why? Because we take its magnitude, we find that it's 1. So let's see. Make a note here. We can make any vector into a unit vector by dividing it by its own magnitude. So one important result relating to unit vectors is that whenever we have any, just any vector in any, size length, we can turn it into a unit vector version of itself by dividing it by its magnitude. So, and if you remember going, if you're asking how we do that, or how does that work, if you remember going back to multiplying vectors by, constant numbers, we remember that the process of doing that, what it looks like graphically, is sort of like a scale or squish. We're pulling it out or pushing it back in when we're multiplying by c. So as it turns out, multiplying a vector, dividing same as multiplying by reciprocal, multiplying by 1 over a magnitude turns out to always be the exact number to squish a vector back down into length 1. So let's say I have vector v, which say it's 2, 2, and I want to find the unit maybe it's better to say I want to express it as a unit vector. So in order to do that, we can imagine, before we start, so x, y, what will v look like? Well, 2 in the x direction, 2 in the y direction. So, da, 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 da. So vector v would look like this. So if I want to find what its turn it into a unit vector version of itself, the way we start is we would divide v by its own magnitude, or 1 over magnitude of v. And quickly, to do that, again, what is magnitude of v? Magnitude of v is going to be square root of this component squared, 2 squared, plus that component squared, 2 squared. So we have square root of 4 plus 4, which is 8. This is equivalent to saying, pull out a 4, so we have 2 root 2. So, therefore, magnitude of v is, v divided by its magnitude will look like v times 1 over 2 root 2. Which, going back to how scalar multiplication works, I just multiply each of these components by that. So 2 times 2 over root 2, 2 times 2 over root 2. Which cancel, 1 over root 2, 1 over root 2. So that is v divided by its magnitude. And I picked this example because, as we can see, we've already shown that 1 over root 2, 1 over root 2 is unit. So you can trust me there. And yeah, we've just essentially, we can see what this looks like graphically is, if I've multiplied v by some number, in this case, 1 over 2 root 2, again, that number is less than 1. So what's kind of happened here is that I sort of shrunk v a bit. In this case, it's like quite significantly, actually. I probably should have drawn the scale a bit differently, but v over its magnitude will actually be a much shorter vector than v, but still in the same direction. So it looks something like this, and it'll have length 1 if you check it. So we're good on that front. Here we go. Instead of talking about angles between vectors, let's just make a new page. Let's actually start with dot product. So, I don't know if I mentioned this explicitly before, but you cannot multiply two vectors in a traditional sense. You can multiply a vector by a scalar number, but not two vectors themselves. There's actually no operation for that. What we can do, however, is we can take a normal product of two vectors. We can take a dot product between two vectors. So, definition. So, dot product is a binomial operation, which just means it takes two quantities. So in this case, it takes two vectors to do it. That sums the products of two vectors components. So what does that mean? Well, we have an example here. Example, let v be 1, 1, 2, 1. Just go back to that. And then u this time will be -1, -1, 0. Switch it up a bit. U dot v is going to be equal to, so let's think about this, the sum of the products of the two vector components. So the way we start doing dot product is I'm going to multiply each of their components together. So there we go. So in this example, first components multiply together, 1, -1, plus second components together, 2, -1, plus third components together, 1, 0. And if we, do this out, 1 times -1 is -1, 2 times -1 is -2, 1 times 0 is 0. So that would be the dot product between u and v. And so for a more, abstracted, formalized example, in R2 and R3, let's say we have u dot v, u dot v. It's going to be the same thing as saying first components multiplied together, plus second components multiplied together. And then in 3 dimensions, I'll draw the dot figure just to show that. They use similar notation, but dot product is, I should say, normal multiplication between two numbers does use the same notation. They both use dots. But the importance here is in the context. We use the dots when, or two vectors imply that it's a dot product. Two numbers implies that it's just normal multiplication. And so in 3 dimensions, again, we just extend it out. 1, u1 times v1 components, u2 times v2, u3 times v3. And this actually works in all dimensions. So in n dimensions, u dot v would look like u1 times v1 plus u2 times v3. And we can imagine going all the way up to n dimensions. Nth component times nth component. So one interesting thing to note here is that, I should even put this in the definition probably, is that previously when we've done vector algebra, there we go. Previously when we've done vector algebra, adding two vectors, multiplying a number times a vector, the result's always been a new vector, right? U plus v is just some new vector, c times v is some new vector. And we've even seen what those would look like graphically. Adding u and v is adding tip to tail, making a new vector. C times v is just squashing or stretching v itself, making a new vector. Excuse me. But dot product actually results in a number. Doing a dot product, as we see right here, that didn't result in a new vector. That resulted in a number. So that's an important thing to keep in mind. Whenever you see the dot product of two vectors, you should immediately be thinking, okay, so the result is going to be a number, not a vector itself. Okay, so let's see. I'll just write a few other notes on dot product. So we should note that u dot product with v is always the same as v dot product with u. And what that really means is just the order in which we do the dot product doesn't matter. It's like, in this example right here, I could have had v times u, but all that would change is the order of, multiplications here. -1 times 1 instead of 1 times -1. So no matter what order it's written in, the dot product of two vectors doesn't change. Let's see. That's true. And let's see. let's say we're doing the dot product of some scale constant. So c times u dot product of v. So, again, c times u is just a scaling of u. C times u dot product with v is the same as saying c times u dot product with v. So again, what this is really saying is that if we're doing a dot product between two vectors and one of them is scaled, I can pull that coefficient out and then do the dot product by itself. So one of the more neat applications of this is, we're going to see in a moment when we talk about angles between vectors, but u dot v, if u dot v is equal to 0, then that necessarily implies that if you look at u and v on a graph, they're actually going to be perpendicular to each other, which, side note, what that really just means is, I should use the colors the other way, but whatever. Say u, say v. We can see graphically these are perpendicular to each other. Well, if you were to find what they are and take their dot product, the dot product would actually come out to be 0. We can do a quick example. So let's say u is, let's see, so that's x, y. So u is 0, 2, and then v is, 1, 0. That's about what they look like. So u dot product with v would be first components multiplied, 0 times 1, plus second components multiplied, 0 times 2. 0 times 1 is 0, 2 times 0 is 0, 0. And I'll just say, you also might hear the word orthogonal. In the context of vectors, orthogonal also just means perpendicular. If two vectors are perpendicular, they're orthogonal. It means the same thing. And then last thing, let's say I have 3 vectors, u dot product with v plus w. So again, v plus w is a new vector, so I'm essentially dot product, doing the dot product of u and this whole vector right here, v plus w. If that's the case, you can always break it up like this. This vector, or this number right here, u dot product v plus w, is the same as this number, u dot product v plus u dot product w. In other words, dot product distributes across vector addition. Let's see, any other big points? I think those are the main points of interest for dot products. Okay, so now that we know what dot products are, we can say a little bit more about the angles between vectors. So, kind of say what it looks like graphically. I'm getting better at this. So let's say we got vector u, and again, this is 2D space, let's say, for visualization purposes. V and u. So when I talk about the angled between two vectors, in this case, the angle between vector v and u. What I'm talking about graphically is, imagine, these are two arrows, almost like line segments that point in opposite directions. Well, if they're two line segments, we can imagine that, they have some angle between them. They even share a starting point. So u and v can be, imagined to have some angle theta between them. And theta in this case would be the angle between vector u and v. So what's important about that? Well, I should say rather, why does that tie into dot products? Well, it's a pretty important formula relating to vectors that says if I have, if theta is the angle, I keep writing angel, between u and v, then, brace yourself for formula. Let's arrange it like this. Cosine of that angle is always equal to u dot product v over magnitude of u times magnitude of v. So that's a bit more of a complicated formula, but it incorporates a couple things that we've been learning about. So again, theta is just the angle between the two vectors, so something like this guy right here, for example. And what we're saying is the cosine of that angle is always equivalent to the number that we get when we take u and v's dot product and divide it by their two magnitudes. So in this example, if u is going to be, let's say, 1, 4, and then v is going to look like, well, let's see. It'd be better to get an example that gives us a recognizable angle, not just some insane cosine. So let's say we have, I don't know, u is going to be 3, 3. V is going to be equal to u is going to be 3, 3, and v is going to be 1, 0. Find the angle between u and v. And, graphically, it's a couple times, but v is going to be, 1 in the x direction, 0 up, so v is about right here. U is going to be 3, 3, so 1, 2, 3. 1, 2, let's extend the graph a bit. 3. What we're looking for is the angle between these two vectors, theta. That's u and that's v. So how do we do that? So let's go back to our formula. We know that the cosine of this angle is going to be equal to u dot product v over magnitude of u, magnitude of v. So let's break that down piece by piece. Let's find their magnitudes first. As we've shown, magnitude of...
You mind if I close the door?
Oh, I'm sorry.
Yeah, just a little. Thanks.
Okay. So, magnitude of v is going to be square root of 3 squared plus 3 squared. So in this case, it'll be 3 squared plus 3 squared. That's 9 plus 9, which is root 18, which is 3 root 2. And similarly, magnitude of v is going to be first component squared plus second component squared, which will just be square root of 1 squared, which is 1, and square root of 1 is 1. So v is actually a unit vector. And then finally, u dot product v is going to be, so if you remember, it's multiplying their components together and then adding all those results. So 3 times 1, 3 times 1, plus 3 times 0, right? First component, second component, second component. So v is going to be 3 times 1 is 3, 3 times 0 is 0, so 0, u dot v is equal to 3. All right, so that means we can, start plugging in now. U dot v is 3. Magnitude of u is 3 root 2. Magnitude of v is 1. So we get 3 over 3 root 2, which, if we do a little bit of simplification, is 1 over root 2. And so finally, if we have cosine of an angle, it's going to be 1 over root 2. I hope we remember this from pre-calculus, but then the angle is going to be pi over 4, or 45 degrees. So that's an example of using the formula to find the angle between two vectors. And then just I'm going to say a little side note right here. You'll sometimes see the formula written like this. U dot v is equal to u times, magnitude of u times magnitude of v times cosine of the angle between them. The reason it's written like this is because if you rearrange this formula, multiply these over, what you now get is a formula for u dot v. So rather interestingly, if we rearrange this formula, we actually make a new formula that allows us to find u dot v without doing, normal dot product operations. So what's it? Yeah, right here. So in this example, if we knew the angle between them off the bat, we wouldn't have to do this process. We could just plug it into this formula. So you will sometimes see it written like this, but just know that this formula right here, just a rearrangement of this one over here. Okay, and then I think finally, and if there's any more, we're still getting the kinks ironed out of this, but if there's any more topics, I'll make sure to add them after the fact. But I think our last main topic is vector projection. So before we get into doing, the formula and doing some work with vector projection, what does it mean to project a vector onto another? Well, let's see. So say we have two vectors, u and v. What it means to project vector u onto vector v is, let's imagine the perpendicular line connecting u and v. So like, for example, u is right here, v is right here, right? Then let's imagine drawing a perpendicular line from the tip of u onto v, such that this line is, perpendicular to v itself, right? So I've just drawn from tip of u down to v a line that's perpendicular to v. Let's say that we can almost think about it as this sort of marking like a section of v. So like, if that perpendicular line happens to hit right here, then let's say we have some new, smaller, almost like a scaled back version of v, a vector in the same direction of v. It's just along v's length, but it's its length itself is dictated by this line we've drawn. So if we can imagine doing that, then this new vector right here is called the projection of u onto v. Or actually, sorry, I wrote those in the wrong order. The projection of u onto v. So that's what this little vector would actually be labeled. Projection of u onto v. And the way you can think about it is, what's more formally said is that the projection of vector u onto v, written as the vector projection u onto v is the, you must think about it as the component of u that is in the direction of v. So we can get more into this in another video, but if we sort of work our way backwards, let's actually imagine that red line we've drawn the perpendicular as a new vector. Well, if I add projection of u onto v plus the perpendicular, so add these two vectors together, resulting in tip to tail, the result is u. So we can almost think about it as u is comprised of its projection onto v plus some vector that's orthogonal or perpendicular to v. That's just the symbol for being perpendicular. So if I'm able to find the projection of u onto v, what I'm essentially doing is I'm breaking u up into a portion of itself that's in parallel to v and perpendicular to v. And, without further ado, the formula for projecting u onto v, creating this new vector, is u dot product v over v dot product v times, v. And just remember here, so like we said before, dot product always results in a number, a scalar. So u dot product v is a number, v dot product v is a number, and then dividing these two together results in just another number. So really, this formula is a constant number times vector v, a scaling of v, like we said before, which is exactly what projection of u onto v looks like graphically. It's some scaled up or down, but in this case, down version of v. Kind of a ghostly v, let's get rid of that. Okay. So we're to do an example, find, and since we're hitting the time limit, let's just use the vectors we've used before. So in this case, 3, 3, 1, 0. So let's find the projection of u equals 3, 3 onto v, which will be 1, 0. So first things first, write down the formula. Projection of u onto v is going to be u dot v over v dot v all times v. Well, what's u dot v? As we shown in the previous problem, u dot v is just going to be 3 divided by, okay, v dot v. So let's think about this. So v is 1, 0, right? So let's see over here. V dot v is the same thing as saying 1, 0 dot 1, 0. And so just because it's v dot v, it doesn't change the process of dot products. We still multiply individual elements and add them together. So in this case, first element times first element plus second element times second element. Times 1 is 1 plus 0 is 0, so the whole thing comes out to be 1. So u dot v over, so u dot v, 3 over v dot v, 1. Times v, and then finally, 3 over 1 is 3. And what is v? Well, it's just 1, 0. So 3 times vector 1, 0 is the same as 3 times 1, comma, 3 times 0. So this vector is the projection of u onto v. And what that looks like graphically, what's happening here, again, let's use that one. So v looks something like this, right? 1, 0, and then u looks something like 1, 2, 3, 1, 2, 3, right there, u, and that's v. If we look at what this vector looks like, projection of u onto v, so 3, 0. So 3 in the x direction, 1, 2, 3, 0 up. We can see that, just like in this scenario, it's some scaling of the vector we're going onto. In this case, we're going onto v, so it's some scaling of v. And we notice that, again, if I were to just look at u and then draw a perpendicular line down into the direction of v, that seems like it would result in projection of u onto v. So I've essentially found a component of u that's parallel to v and one that can be perpendicular to v. All right, so we're brushing up on the hour and 10-minute marks. I'm going to call it quits for today. And if there's any other sections that I've missed, we're still getting the kinks out, worked out on which notes need to cover what. I'll add that in post. So thank you and good day.